Thank you, Ross. So far this session has focused primarily on predicting seismicity, but in order for such forecasts to be useful to the user community, you also have to forecast the shaking that results from this seismicity. This work is done in collaboration with my advisor, Tom Jordan, Ned Field at the U.S. Geological Survey, and I'm also using using big models that have been contributed by large collaborations, the Working Group on California Earthquake Probabilities and the CyberShake collaboration. I'm going to start by discussing the UCERF3 long-term and ETOS models, as well as the CyberShake model. I'll also discuss the treatment of ruptured directivity as aleatory variability in the ground motion prediction equations and long-term CyberShake. I'll discuss the coupling of the UCERF3 ETOS model and CyberShake. And finally, I'll show some examples of scenario operational earthquake forecasts following magnitude 6 Parkfield and Bombay Beach earthquakes in California. So UCERF3 stands for the Uniform California Earthquake Rupture Forecast, version 3. The time-independent model is the California component of the 2014 National Seismic Hazard Maps. There's also a long-term time-dependent model currently in press at BSSA. It's a Brownian passage time renewal model. About 15% of the fault sections in the model, including most of the San Andreas, have an explicitly set date of last event, and the rest use a historical open interval based from 1875 to constrain the renewal model distribution. And this long-term time-dependent model results in maximum 30-year probability gains on the order of about 2 times, which is on the southern San Andreas fault. Before I discuss the UCERF3 ETOS short-term model implementation, I want to mention some of the limitations of the prior step-type models that have been implemented in California that we're trying to improve upon. You see an example here of the step forecast that was operational at the USGS for California. So one of the limitations is that the probability of triggering a large damaging aftershock is independent of the proximity to major faults. And another limitation is that it lacks elastic rebound, so the greatest probability for any given rupture is actually the moment after that rupture has occurred, a complete re-rupture. UCERF3 ETOS is a fault-based epidemic type aftershock sequence model. Unfortunately, I don't have time to go into a lot of details on this model, and it deserves its own talk, but it merges the point process spatiotemporal clustering models that many of you are familiar with the UCERF3 finite fault model. So you can have off-fault or subseismogenic aftershocks or Mainshocks that trigger fault-based superseismogenic ruptures and vice versa. It also includes elastic rebound for the superseismogenic fault-based sources. And in fact, if you disable this feature, you will get runaway sequences of events where ruptures keep triggering themselves. And this also generates synthetic catalogs of events. Here are some examples of these catalogs for a magnitude 6 Parkfield scenario. You can see the Mainshocks surface in red here on the top. The top is a typical sequence where there are a number of subseismogenic and off-fault aftershocks. On the bottom is an extremely productive sequence where the Parkfield earthquake triggered a superseismogenic fault rupture on the San Andreas going down through the Mojave section and many subseismogenic and off-fault aftershocks. Turns out for the single day following a magnitude 6 Parkfield scenario, about 3 out of 1,000 simulations produced a superseismogenic fault-based aftershock, although most were less productive than this example that I show on the bottom. And the next step is to generate an operational earthquake forecast from these catalogs. So we generate suites of synthetic catalogs, in this case 100,000 for each scenario, to determine the trigger rate for each fault rupture. And the trigger rate is just the number of simulations in which that rupture occurred divided by the total number of simulations. Then you can calculate a short-term probabilistic hazard map where the rate of each rupture is the long-term rate, which might have to be modified for elastic rebound, plus this short-term trigger rate. Now, typically, this type of forecast would be combined with an empirically based ground motion prediction equation. But these ground motion prediction equations have some limitations. First of all, there's very few data for large magnitudes and also at short distances. And there's also high scatter, which is treated as aleatory variability. For this work, we're replacing the ground motion prediction equation with the CyberShake completely physics-based hazard model. The CyberShake model takes the earthquake rupture forecast, in this case UCERF, and extends each rupture with a suite of what we call rupture variations. Each rupture variation has its own hypocenter and slip distribution. And then we run a full 3D deterministic wave propagation simulation, actually using seismic reciprocity, to get two-component seismograms for every pair of sites and rupture variations. These seismograms can then be combined into a hazard curve and eventually into a hazard map across a region. For this particular study, we used a CyberShake model with 283 sites in the greater Los Angeles region. CyberShake has so far only been computed using the UCERF2 ruptures. So for this study, I take the UCERF3 ETAS methodology and apply it to the UCERF2 rupture set. This results in about 415,000 rupture variations per site and a total of 235 million seismograms per model. So it's a very large model that requires significant high-performance computing resources. This just shows the importance of a 3D velocity structure in the CyberShake calculations. On the left is a calculation done with CyberShake but using a simplified one-dimensional velocity structure. And on the right is the CyberShake model that we're using here, which is the latest SCEC model, CVM S4.26. Now, I mentioned earlier that there's high scatter in the ground motion prediction equations that's treated as aleatory variability. One of the components of that scatter is ruptured directivity effects. One thing that I'm showing here is two almost identical ruptures on the southernmost San Andreas fault from the SCEC TerraShake simulation. So both magnitude 7.7 ruptures. The rupture on the left has a hypocenter at the southeast of the fault near Bombay Beach, and the rupture on the right has a hypocenter at the northwest of the fault. And you can see that these two different scenarios result in very different ground motions in the Los Angeles basin. Now, if we were somehow able to forecast this type of directivity, we could reduce the aleatory variability in the ground motion prediction equations, but we can't currently do that for long-term forecasting models. But as we'll show, we can actually do that for short-term models. And it turns out for CyberShake, all of these different scenarios are incorporated as different rupture variations and treated equally. So putting it all together, we can combine the pre-computed CyberShake ground motions with the short-term forecasting model of UCERF3 ETAS. So we take the fault-based ruptures that are triggered in ETAS catalogs and raise not only the rate of that rupture, but we raise the rate of the ruptures with the hypocenters that were triggered in the ETAS models. So this short-term forecast localizes epicenter probabilities. So for example, if there is a swarm of seismicity near Bombay Beach in the southern end of the San Andreas Fault, not only has the probability increased of a rupture on the southernmost San Andreas, but the probability of a rupture on the southernmost San Andreas with a hypocenter near Bombay Beach, which I previously showed as being the worst case for the Los Angeles basin, has increased. And finally, for some results, what you're seeing here is a one-day hazard map for Los Angeles. It is the probability of exceeding 0.2 Gs of 3-second spectral acceleration, computed using CyberShake and this is the long-term time-independent model. And it's on a logarithmic scale. This is that same map, but for a single day following a Parkfield magnitude 6 earthquake using the UCERF3 ETAS methodology. As you would expect, there are much higher probabilities along the San Andreas Fault, but there are also much higher probabilities in the Los Angeles and Ventura basins. This is the same thing, but for a Bombay Beach magnitude 6 scenario earthquake in the area of the 2009 swarm. Similarly, we see an increase in the Los Angeles basin, San Bernardino area, and the Ventura basin. This is a gain map from the short-term operational forecast to the long-term model. Yellow is about a factor of 10 increase in probability, and the darkest red is a factor of 100. And we can also compare these results to those computed using ground motion prediction equations that include side effect terms such as VS30 and basin depth, but do not include ruptured directivity or directivity basin coupling. And that's shown here. These are gain maps. And as you would expect, they are very smooth, mostly centered around the fault. You can see the basins light up a little bit due to inclusion of the VS30 and basin depth terms, but you don't have the strong increases in the basins that we see with the CyberShake model. Here are some hazard curves. The top one is for San Bernardino, which is in soft, deep sediments very close to the San Andreas Fault. There is the blue curve is the long-term time-independent model. Green is the long-term time-dependent model. So you can see that the scale of change for the long-term time dependence is fairly small. And then red and orange are the Parkfield and Bombay Beach scenarios that I've just mentioned. And it's about an order of magnitude increase in probability along for all of the curve. This is a log-log plot. And the bottom is a similar plot in the middle of the Los Angeles basin. So in summary, fault-based operational earthquake forecasting models such as UCERF3 ETAS address some important limitations in prior models. Additionally, directivity, which we cannot forecast in long-term models, can be forecast in short-term clustering models. And this results in significant probability gains in the Los Angeles basin following magnitude 6 ruptures near Parkfield and Bombay Beach. And finally, while the CyberShake model requires significant HPC resources, pre-computed ground motions can be rapidly combined with UCERF3 ETAS as a post-processing step, and such forecasts could be generated daily. Thank you very much for your attention.
Questions for Kevin? Yes, Matt?
In our work in New Zealand and going national with our OEM model, we're not quite ready to make the jump to the ground motion simulations, and we're using GMPs. And we're finding that particularly when you have a large Mainshocks, you're getting such high rates of aftershocks that it's driving the GMPs out into uncertainty space into ground motions that we don't necessarily believe, and we're just trying to figure out how to deal with that now. Do you plan to go through this exercise?
Need to repeat the question.
And with GMPs, or is this something that you've thought about?
Could you repeat the question?
I think Matt said that GNS Science isn't ready to go to a CyberShake approach, but I wasn't quite clear what your question was for Kevin.
So we're finding that using GMPs, we get high rates. So when we do our OEF model, you get a large main shock, you get lots of aftershocks. So then you're really sampling far out into your uncertainty space on your ground motion prediction equations. So it's driving up quite high ground motions.
So the aleatory variability is very important. Yeah, I would assume I would assume that.
Do you plan to go through the same exercise using the standard GMPs?
So using GMPs that incorporate ruptured directivity, for example, or Yeah, well, I did that using the GMPs that I have access to, which don't include directivity. But it would be interesting to see if using a GMP that included ruptured directivity could further reduce the aleatory variability in these short-term models. And I would imagine it could. It wouldn't be able to capture all of the 3D effects that the CyberShake model accounts for, but I think it would be an improvement over just the simplified models.